11.2 relativity of time, length, and momentum. Okay, when we have a relativity means that if when you have a spacecraft, for example, moving with a speed close, the speed of the spacecraft is close to the speed of light. You know, the speed of the light is 9 × 10⁸ meter per second. So we have interesting phenomenon happening. So looking at this, you have a two plate. So one of that emit the light and it travel to the second plate and will be reflected back and come again here. So the total trip that you can measure in a spacecraft is delta S when the wave from one plate hits another plate. And the reflection, if you measure the reflection, the time of the reflection would be the same time of the going up. It would be the same time as it go down, right? The total time is 2 delta TS. The delta TS is the time that you measure from inside the spacecraft. Now imagine that someone else, when the spacecraft now is moving with close speed to speed of light. Now this spacecraft is now moving. Someone outside from the Earth it has a clock and measure the traveling time. What the person sees is that the wave is traveling in this shape, hitting the upper plate and then going to the reflected back to the lower plate. So since the spacecraft is moving, he will observe this kind of path. But someone inside the spacecraft will see this is just simply go up and go back down. Now, according to that, so here is depicted. So c delta t, the speed of the light multiplied by time would be that length. Also, someone outside, the speed of the light is again c, and the time measured on Earth is delta tm. And from here to here is your spacecraft, the distance the spacecraft moved from the observer outside on Earth. So we are moving at the speed of v, and here is delta t, and the delta tm is measured on the Earth. Now, here we have a right angle triangle. We can use the Pythagorean theorem. V delta Tm to the power of 2 plus C delta Ts power 2 is equal to C delta Tm power 2. This is what we have. We can rearrange it. We can bring the V delta Tm to the other side, power 2 each term. Then you can divide each term by C power 2. Divide each term by C power 2. So C power 2 divided by C power is canceled. V power 2 divided by C power 2. And here is C power 2 is canceled. Delta Tm power 2, you factor it out. You get 1 minus V power 2 over C2 is equal to delta Ts power 2. You square root both sides. This going under a square root, the power 2 cancel. You rearrange it for delta Tm, and this is what we have. V is the velocity of the spacecraft again. Delta Tm is a time that measured on a stationary observer on Earth, and delta Ts is the time measured on a spacecraft. So here is a question. An astronaut whose pulse frequency is 72 beats per minute descent voyage, what would her pulse speed relative to Earth when ship is moving relative to Earth at 0.10 c and 0.9 c? C is the speed of the light. So since I want to take a time this is the frequency, I want to turn it into the period, which is the unit of that is time, right? So delta t is 1/72. This is a pulse that is measured on a spacecraft, right? So as 1/7 is 0.014 minutes, then velocity of that spacecraft is 0.1 c. So instead of v power 2, I put 0.1 c power 2. So c2 by c2 cancel, and 0.1 power 2. 1 minus that, you just put in your calculator. Delta ts is the period that the astronaut inside the spacecraft measured. Put it there, and you know the delta t, I'm going to be 0.014. If you do the same thing with 0.9 c would be the velocity of your spacecraft, you get 31 beats. So 0.9 compared to 0.1. 0.1 c is not a close velocity to speed of light. When your velocity is very close to the speed of light, you will see the time dilation. Means the time that you observe on Earth will be different than the time the person observed on a spacecraft. The time dilation happens. So for practice, you can do question number 2. So here is a twin paradox. If we say there is a twin on Earth, one of them is want to travel with a shuttle, and the shuttle is moving with the closest speed to the light. When it's go a round trip and come back, this twin is still young, but this one is getting old. It means the time very different for both of this. If the time, for example, he feel the time is 1 year past, but the person here will feel the time to be 100 years. So this is a time dilation. Now length contraction. So for the length contraction, we have L of m is equal to L of s square root of 1 minus v2 over c2. You see the L of the m is a spacecraft observer that you have. So it means if you measure a stick on a spacecraft and you observe it from Earth, you will see this is shorter. The stick on this bird is shorter. But you will see the stick on a spacecraft to be kind of the same length as normal. So let's just look at the question. A UFO heads directly for the center of the Earth, 0.5 c is the velocity of the spacecraft. When it passes to communication satellite, it's satellite orbiting at 3.28. So this is the one that actually it is observer on Earth, right? See that. What is the altitude of the UFO at the instance it determined by the pilot? I want to find, of course, this distance that when a pilot is moving with the speed, right? We'll see this distance to be contracted. So it's kind of L of m. Your L of s is 3.28, and then you calculate it, you put the v to be 0.5 c, c and c canceled. It's going to be 2.84 10 power 3, which is smaller than that. So if we expect it, because the spacecraft is moving, so it will see the distance outside to be shorter than actually what is observed by the stationary observer. So spacecraft traveled past Earth with a speed of 0.87, so it's v, and measured, version of the Earth is measured, especially traveling past with the Earth is measured to be 48 meters long by observer on Earth. So basically, this is the length that is contracted, because you see that the spacecraft has 48 meter length. The spacecraft is moving. This is not actual. You see a contraction of that length. So basically, the L of the m is given. Now, what is the proper length of the spaceship? So proper length, which is ls, just rearrange it for ls, and you just calculate it. So that would be the proper length, which is bigger actually than what you observe. For the relativistic momentum, you have mv square root of 1 minus v2 over c2. See that the rest mass is m. So when it's not moving at a speed close to velocity of light, this is non-relativistic momentum. But the relativistic momentum is here. The m, this one, m divided by square root of 1 minus v2 over c2, this is relativistic mass. The mass from the observer outside, like watching a spacecraft, and the spacecraft moves with the speed of the light, the observers see that the weight of this object is increasing. Here is some question. Linear accelerators accelerate charged particle to nearly the speed of the light. A proton accelerates 0.99 c. So this is the speed of that. V. Determine the magnitude of relativistic momentum. So we know the formula m of that. You can look at the appendix. The velocity is given. Just so for p, this is the p. And part B said, make the reference to the non-relativistic and compare it. So MV is that. You see that the P relativistic is much more than the P non-relativistic. The reason is that when it's moving with the speed of closest speed of the light, it's the P are heavier compared when it's not moving close to speed of light. So you can do question number 10 for practice here.